So spontaneity. The first law of thermodynamics tells about the relationship between the heat absorbed and the work performed on or by the system. It puts no restriction on the direction of heat flow. That is, however, the flow of heat unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. That's mean, for example, a gas is expanding to fill the available volume, burning carbon in the presence of oxygen to give carbon dioxide. So, but heat will not flow from colder body to warmer body on its own. The gas is a container will not spontaneously contract into one corner of corner, or carbon dioxide will not form carbon and dioxygen spontaneously. So these and many other spontaneously occurring changes shows unidirectional change. See, we may ask, what is the driving force of the spontaneously occurring changes? What determines the direction of the spontaneous change? So these things we will discuss here. First, understand what do we mean the spontaneous reaction or the change. First, you may think by your own common observation that spontaneous reaction is one which occurs immediately when contact is made between the reactants. So the combination of hydrogen and oxygen gas, combination of hydrogen and oxygen gas. So these gas may be mixed at room temperature and left for many years without observing any perceptible changes. So although the reaction is taking place between them, so it is an extremely slow rate. So this called spontaneous. That is called spontaneous reaction. So the spontaneity means having the potential to proceed without the assistance of external agency. So this is called spontaneous. However, it does not tell about the rate of the reaction or the process. Okay. See, that these cannot reverse their direction on their own. So that means the spontaneous process is an irreversible process and may only be reversed by some external agency. First, we'll see, is decrease in the enthalpy a criterion for spontaneity? Now see, they examine the phenomenon like flow of the water down or fall of the stone on the ground. We find that there is net decrease in the potential energy in the direction of change. So by analogy, we may be tempted to state that the chemical reaction is spontaneous in a given direction because decrease in the energy has taken place, the exothermic reaction. For example, half moles of N2 gas react with 3/2 moles of hydrogen gas to give what? Ammonia gas. So here the enthalpy of a reaction is minus 46.1 kilojoule per mole. Similarly, half moles of hydrogen gas react with half moles of chlorine gas gives HCl gas. So here the enthalpy of a reaction, that is standard enthalpy of a reaction, is minus 92.32 kilojoule per mole. Similarly, in hydrogen gas react with half moles of oxygen gas. 1 mole of hydrogen react with half mole to give H2O liquid. Here the reaction standard reaction enthalpy is minus 285.8 kilojoule per mole. So these the decrease the enthalpy in passing from reactant to products like this. See, you can I will draw one diagram. Look at this diagram. This is enthalpy for exothermic reactions, and this is enthalpy for endothermic reaction. Look here, the decrease in enthalpy that's mean that in passing from reactants to product. So reactants to products passing from. So there is the exothermic reaction that's postulate driving forces of a chemical reaction may be due to the decrease in the energy sound reasonable as the basis of evidence so far. Okay. Now we can examine the reaction like half moles of N2 gas react with 1 mole of oxygen gas to form NO2 gas. So here the enthalpy of a reaction is plus 33.2 kilojoule per mole. Similarly, one more reaction, carbon graphite. That is the solid form. 2 moles of the sulfur, the liquid form, to form carbon disulfide liquid. Here the energy of the enthalpy of a reaction is plus 128.5 kilojoule per mole. So this reaction here, look at this. Here, this is the total energy of the reactant. This is the total energy of the product. So here in between these, the reactant and product, that is the enthalpy of a reaction. Net heat is evolved in this reaction. This is for exothermic enthalpy diagram for the exothermic reaction. Suppose in endothermic, this is exothermic. In endothermic, mean the reaction though endothermic or spontaneous, the increase in the enthalpy. Look at this, the reactant to product. This means it becomes obviously that a decrease in the enthalpy may be contributed factor from spontaneously, but it is not true for all cases. Okay, look here, the enthalpy of product, total energy of a product. Here this is total energy of the reactant, and this is enthalpy. So the net here the enthalpy of a reaction, that is net heat absorbed from the surroundings in the reaction. So this is the endothermic process, enthalpy diagram for the endothermic process. This is for the exothermic process. Then entropy and spontaneity. Entropy and the spontaneity. See here, what drives the spontaneous process in the given direction. So now examine such case in which the delta H is equal to 0, that is enthalpy change is equal to 0, means there is no change in enthalpy, but still the process is spontaneous. So let us consider diffusion of the two gases into each other in closed container vessels, which is isolated from its surrounding. Look at this two diagram. This is diffusion of two gases. The two gases are A and B. Here the green color dots and the blue in color dots. So A and the B. So here and respectively here that's been separated here. They separated by the movable partition. So when the partition is withdrawn, look at this. The partition is withdrawn, the gases being to the diffuse into each other and after a period of time, so diffusion will be complete. After a period of time, diffusion will be complete. So let us examine the process before the partition. This is the before the partition. If we were to pick up the gas molecules from left container, so we would be sure that these will be molecules of gas A, and similarly we were to pick up the gas molecules from right container, that will be B. So but if we were pick up the molecules from container when partition is removed, look at this, we are not sure whether the molecules picked up gas A or gas B. So we say that the system has become less predictable or more chaotic. And we may now formulate the another postulate, that is isolated system. There is always tendency for a system energy to become more disorder or chaotic, and this could be criterion for the spontaneous changes. So at this point, we introduce the entropy, that is the another thermodynamic function that is called entropy. The symbol is S. Here, this that is the disorder in the manifestations of entropy, that is that to form a mental picture, one can think of entropy as a measure of the degree of randomness or disorder in the system. So the greater the disorder in the isolated system, the higher the entropy. So entropy will be higher. That is, as far as chemical reaction is concerned, that this entropy change can be attributed to the rearrangements of atoms or ions from one pattern in the reactant to another pattern. That means the products. If the structure of the products is very much disordered than the reactant, there will be a resultant increase in the entropy. Okay. So the change in the entropy accompanying a chemical reaction may be estimated qualitatively by a consideration of the structure of these species taking part in the reaction. So decrease of regularity in structure would mean increase the entropy. For a given substance, the crystalline solid state is the state of lowest entropy, the gaseous state of the highest entropy. Now let us try the quantify entropy. One way to calculate the degree of disorder or chaotic distribution of the energy among the molecules would be through the statistical method, which is beyond the scope of this treatment. See, other way would be relate this process to heat involved in the process, which would be make entropy a thermodynamic concept. So entropy, like any other thermodynamics properties such as internal energy like U, and the enthalpy H, and the state function, this is a state function, and the entropy, change in entropy is independent of path. So whenever heat is added to the system, it increases the molecular motion, causing increased randomness in the system. So that's mean the heat randomness influence on the system. Okay. Here, look at this. The temperature is measured. That means a system having a higher temperature has greater randomness. Higher temperature means randomness is greater. So that means the lower the temperature. So that means that the temperature is the measure of average chaotic motion of the particles in the system. So heat is added to a system at lower temperature causes greater the randomness. So randomness is greater. Just randomness. You can also say. So here then the quantity of heat is added to higher temperature. This means higher temperature. So this is such that entropy changes inversely proportional to the temperature, so that delta S relate with Q, heat and temperature, for a reversible reaction. So delta S is equal to Q reversible divided by T, because this is inversely proportional to the temperature. The entropy change is inversely proportional to the temperature. Then the total energy change for the systems and surrounding a spontaneous reaction is delta S total is equal to delta S system plus delta S to the surrounding is greater than 0. So when a system is in equilibrium, the entropy is maximum. So the change in the entropy, that means what? Delta S is equal to 0. So we say that the entropy for a spontaneous process increase till it reaches maximum, and at equilibrium change in the entropy is 0. So since the entropy is state property, we can calculate the change in entropy of a reversible process by, that is, delta S of a system is equal Q reversible, that is Q system reversible, Q system reversible divided by T. So if we find both reversible and the irreversible expansion for an ideal gas under the isothermal condition, that's mean here delta U is equal to 0, but delta S is equal to, that is delta S is total, that is this means systems plus surrounding. Okay, this is systems plus surrounding. That means it's not 0 for irreversible process. This here the delta U does not discriminate between the reversible and the irreversible process, whereas delta S does. Okay. Gibbs energy and spontaneity. Here the entropy change, that is the total entropy change, decide the spontaneous of the process. But most of the chemical reactions fall into the category of the either closed system or in the open system. So therefore most of the chemical reactions are changes in both enthalpy and the entropy. See, that's mean neither decrease in the enthalpy nor increase in the entropy alone can determine the direction of spontaneous change for the system. So for this purpose, we define a new thermodynamic function, Gibbs energy or Gibbs function, that is indicate the symbol as G. So here Gibbs energy is equal to H minus Ts. The Gibbs here, the G extensive property and the state function. So the change in the Gibbs energy for a system, we can write it delta G is equal to delta H minus T delta S minus S delta T. When at temperature is constant, so delta T is equal to 0. So the equation will be delta G is equal to delta H minus T delta S. See, this equation is called Gibbs free energy equation. Very important equation. Look at this. So here the Gibbs energy change is equal to enthalpy change minus entropy change into temperature. So this is called Gibbs equation. Then the already see, if you analyze, there is, we find that delta G has units of energy because both delta H and T delta S are energy terms. Since the T delta S is equal to Kelvin divided by joule per Kelvin, so that it will become joule. So here now we consider the delta G relates to this reaction spontaneity. That means delta S total is equal to, already we know, delta S systems plus delta S surroundings. So if the system is thermal equilibrium with the surrounding, then the temperature of the surrounding is the same at the system. So also increase the enthalpy of surrounding is equal to decreasing the enthalpy of the system, so that the entropy change of surrounding is entropy changes of surrounding is enthalpy change surrounding divided by temperature is equal to negative minus, that is delta H systems divided by T. Here entropy of total is equal delta S change in entropy of system plus minus delta H systems by surrounding. So rearranging this equation, that is T delta S that is for total, T delta S total, this is total, is equal to T delta S minus delta H systems. This is also systems. So the for a spontaneous reaction process, the delta S total is greater than 0. So this T delta S of a system minus delta H of a system is greater than 0. This means minus delta H of a system minus T delta S system, so it's greater than 0. You can write as like this. So here using of this Gibbs energy equation, you will get that as delta G is greater than 0. That means minus delta G is the greater than 0, so that the delta G is equal delta H minus T delta S is less than 0. Here the delta H system is enthalpy change of a reaction, and T delta S is a energy which is not available to do useful work. So the delta G is net energy available. So net energy available to useful work for the measuring of the free energy. For this reason, it is also known as the free energy of the reaction. So delta G gives a criteria for a spontaneity at constant pressure and temperature. First, we'll here delta G is negative. That means the process is spontaneous. Here I will write, when the delta G is negative, the process is spontaneous. If the delta G is positive, the process is non-spontaneous. That means this is here less than 0, this is greater than 0. See here, the next is the Gibbs energy change equilibrium. Gibbs energy change and equilibrium. See here, the sign and magnitude of free energy change of the chemical reactions allows. The first one is the predictions of the spontaneity of the chemical reaction, and another one is the prediction of the useful work that could be extracted from it. So far we have considered the free energy changes in irreversible reaction. Let us now examine the free energy change in reversible reaction. So the reversible, under the thermodynamics, there is the thermodynamics and the special way of carrying out a process that the system is at all times in perfect equilibrium with its surroundings. When applied to a chemical reaction, the term reversible indicates the given reaction can proceed either direction simultaneously, so that the dynamic equilibrium is set up. So this means that the reaction in both directions should proceed with a decrease in free energy, which seems impossible. So it is possible only at equilibrium the free energy of the system is minimum. If it is not, system would spontaneously change to the configuration of lower free energy. So the criterion of equilibrium is A plus B gives, that is equilibrium, C plus D, so that delta reaction, delta G for a reaction is equal to 0. Here the Gibbs energy for a reaction which all reactant and products are standard state, so that you have to use that is 0 means delta R G naught is equal to delta R G naught equal to RT ln K is equal to 0. That means here the reactants and product in the delta G standard state is related to the equilibrium constant of the reaction, so that like on rearranging this equation, that is delta R G naught is equal to minus RT ln K. So R you can write it delta R G naught reaction. This conversion of ln to log, you have to multiply minus 2.303 RT log K. Okay, so this is also one of the equation for finding the equilibrium change. So thus then we know that delta reaction, the standard Gibbs energy for a reaction is delta H naught minus T delta reaction for a entropy. So that's equal to minus RT ln K. So for strongly the endothermic reaction, the value of the reaction enthalpy may large and positive. So in such case, value of K, that value of K will be much smaller than 1, and the reaction is unlikely to form much product. So in case of the exothermic reaction, here the delta RH, there is a delta RH, there is a reaction enthalpy is large and negative, and the Gibbs energy change likely to be large and negative too. So in such cases, K will be much larger than 1. Okay, we may accept strongly exothermic reaction to have a large K value, and hence we can go to the near completion. So that the reactions of Gibbs energy change also depends on the reactions of the thermodynamic entropy process. The change in the entropy of a reaction also taken into account. So the value of K or extent of a chemical reaction will also be affected. So depending upon whether this is delta S positive or negative, then that's mean this is it is possible to obtain. Look this. It is possible to obtain an estimate of delta G naught, that is standard Gibbs energy, from the measurement of the delta H naught, the standard enthalpy change, and the entropy change. So in the calculate, we can calculate the K at any temperature for economic yields of the product. Then if K is measured directly in the laboratory, value of delta G naught at any other temperature can be calculated. We will see numerical in this section. Next video we will see the numericals.